So, we'll take a poll whether you want the presentation, the FEA project presentation. Do you want to do it in the class in front of your colleagues, or you want to record a video and upload to Nexus, just like the video you saw for the previous term? So there is a video somewhere here, sample term project video presentation. So 10 to 15-minute video presentation. Do you prefer the remote video presentation or in front of your class? So please raise your hands who prefer to present it in front of the class. All right. Who has no preference? You're okay with either remotely or? All right, so we will do it in class. Majority is in class. So next Wednesday, each team 10 to 15 minutes. So if you open the project guidelines at the very top, close to the announcements, the project guidelines, what are the things I'm looking for in the presentation? Introduction, just objective of your work. Has it been done before? FE model details, the geometry, material properties, boundary conditions, aspect ratio, the mesh quality, and the results and discussion. So does the results make sense? Do you have any experimental data to compare with, or you have any analytical data? I'm not forcing you to compare it with either experimental or analytical solution, but if you have something, you could include that in your results and discussion. At least whether the results make sense. That's what I'm looking for. And so when you're presenting the results, make sure, say if it's temperature, you're showing it in terms of an integer, not some engineering mode. So for example, 2.1 into 10 power 2, no one understands it. So show it as 210 degrees centigrade or something. So present your work so that someone within the 10 minutes, they can understand your results. And discussion, whether the results make sense or not, as per your boundary conditions, whatever you tried, whatever you set out to do, are you observing the same thing in your results? And conclusion, what have you learned, and what do you plan to do with that results in future? So usually the last year, because it was recorded presentation, I asked the students to upload it to YouTube. So they were all senior engineering students, so they used it as a advertisement for their job search. You could think of in those terms too. Your presentation, you can practice in front of a video, record your presentation, your team members. So make sure you have equal contribution, all of you. Record it yourself, and you can upload to YouTube. And Wednesday, the start of the class, we will have the project presentations, and then we'll cover some Gaussian quadrature if you have time. So we have 4 teams, I think, right? Or 5 teams, I don't remember. So we should be done very quickly within 1 hour. So next Wednesday, that's the last day of class. All right, so any questions on the project? So we can meet tomorrow. I have office hours 2 to 5:30, so send me an email. We can also meet over the weekend, Saturday, Sunday. So if you have any questions, we can discuss. Send me a Zoom link and we can meet over Zoom. We don't have to meet personally. So all of these computers have Zoom and also Abaqus. So you should be able to share your screen and show me the Abaqus. And if you're having any trouble, I can help you out. All right, so for today, the agenda is tensile testing. So please download the sketch plate revision 2. So that's the Abaqus fracture exercise. You can have this open. So that's the first exercise we are doing, tensile testing on a dog bone shape. Then probably on a Monday's class, we'll do the fracture on wind turbine. So first we'll understand everything about fracture, and then we'll go to the complicated geometry part, wind turbine on Monday. So today we're just doing it on the simple dog bone shape. So download the sketch plate revision 2. It's an IGS file. So Chrome tries to open it. So go to this 3 dots at the right top corner, more tools, save page as. So download it somewhere. It's downloading to downloads folder as of now. Save it. Go to that folder where it is saved, downloads folder. So if you can't see that extension, go to view. At the top, you have a view. Make sure the file name extension is checkmarked. Then you can see the extension as .igs.txt. So right click and rename the file. Remove the .txt and hit enter. It asks you, do you want to change the file name extension? Say yes. Otherwise, Abaqus, you can't import this file if it has .txt extension. So copy this or Control X. Go to your temp drive. So this PC local disk C temp. So create a folder there in your temp drive, new folder, fracture 21 and your initials. There's already there are some fracture exercises from last year. So fracture 2021 and your initials, underscore your initials. Go into the folder and place that IGS file in there. Everyone's able to do that? So open Abaqus CAE from your start menu. Search for Abaqus CAE, open. So once Abaqus opens with standard or explicit model, file set work directory, file set work directory, use the folder icon to the right, select the folder you just created. Just one click on it, don't go inside it. If accidentally you go inside it, come out using the go up one directory. Just left click once on the folder and say OK. So it should the path should appear there, C temp, and the folder name you gave. Everyone's able to do that. So if you set that for the first time, you won't have any problem finding your results file. So file, import. So we're going to import sketch. So file, import sketch. So go to the drop down and choose IGS. And double click on this IGS file. I'm going to leave everything default. as per IGS scale factor 1. I've used meter scale to model that sketch. I'm going to leave everything same. Say okay. So once you do that, if you scroll down on your tree, at the end you will see the sketches of 1. Or if you go to the sketch module from your drop down, if you go to the sketch module and you will see the drop down, you will see the sketch you created, sketch you brought in. So it's good to bring in IGS sketches so we can do the extrusion here. Then we will avoid all the unnecessary geometry repairs. So bring it as a sketch and extrude or revolve or whatever you want to do here. Yes.
Can you do that first step? Abaqus is
Okay, no problem. So have you set the work directory?
oh, yeah, I did.
Okay, so file, import, sketch, and choose the format as IGS from the drop down. And you should be able to see that file. So that's why we set the work directory beforehand. So it points to the correct folder. And double click on it. And it should go to your, at the bottom of your tree. If you double click that, that's the part you just brought in.
You have all the default selections and that thing.
Yeah, everything default. I didn't change anything. I said, okay, okay. So we'll create a part. So go to part module. So the plan is to do 3 types of study. I've written that here. I can't understand my own handwriting, so I'll write that again. So we'll do 3 cases. Pre-existing crack, stationary. So the crack is not growing. Stationary means not growing crack. And why would anyone do this is, the objective for this is to measure the stress intensity factors K1, K2, and K3. What are those 1, 2, 3? Anyone remembers from last class? K1, K2, K3 are stress intensity factors. They are just amplifications, right? Irwin's formula. K1 is beta times sigma root pi a. So this would have been the stress if there was no crack, but this stress got multiplied with this beta times root pi a, where a is the crack length. So it got amplified, and that's the stress intensity factor. What is 1, 2, and 3? Anyone remembers? Yes, Hayden. Yes, they refer to different modes, right? So mode 1 is the opening mode. So imagine this is a crack surface, this is another crack surface, this palm is a crack surface. Mode 1 is opening mode. So imagine tensile load applied at the bottom and at the top. So the crack is opening up like this. That's the mode 1. And the intensity, stress intensity factor, the amplification of this remote stress at the crack tip is given by beta times root pi. That's the Irwin formula. Extremely accurate for mode 1. This is mode 1, opening mode. What is this mode? Anyone? If these two are crack surfaces, what is this mode? Shear, right? And what is that? Is it mode 1, 2, or 3? It's not mode 1. We just discussed mode 1. This is mode 1, opening mode. 2 is this way, sliding. 2 is sliding. Let me show you the slides. So those are the different modes. in which the crack would propagate. So mode 1 is the opening mode because of tensile load. That's the most dangerous and most common mode. Mode 2 is sliding mode. So something like this. The crack surfaces, they're moving like this. And mode 3 is out of plane or shear or tearing mode. So those are the stress intensity factor or the magnifications at the crack tip because of those different modes. And usually we have mixed mode, the combination of mode 1, mode 2, mode 3. So our goal here, the first exercise we are doing on this tensile dog bone shape is a stationary crack. So we will create a crack of certain length and will not allow it to grow. We just want to see for a given loading how much it gets amplified, and we'll measure the K1, K2, K3. So the Irwin formula is good only for the mode 1, extremely accurate. The other modes, they're not that accurate. The second case we would do is pre-existing crack, moving, meaning growing. Crack would propagate, and we can't measure the stress intensity factors for this. So for this study, usually we want to see in which direction the crack propagates, the direction of the crack propagation. So the third study is no pre-crack. So no pre-crack. So we'll let the analysis figure out where to initiate the crack. Cracks usually initiate as voids. At certain locations, it starts as voids. Wherever the stress concentration is more, at that location, it starts as voids. All of these voids join and form a crack, and that's how it propagates. So we will not create the crack. We will not force the solution. Whatever the conditions are right for the formation of crack, wherever it happens, that's where the crack will initiate. And this is the most realistic case, no pre-crack. Let the crack initiate at the right location and propagate in the right direction based on some set of criteria we're going to give. So those are the 3 studies we will do today on the same geometry. So let's save this file as file, save as. So we have 3 studies. So we'll name them. So first one is pre-crack, and I'm saving this as a CAE file. File save as. Frank, you came late, I think, right? Okay, let me save this and I'll email you this file. Pre-crack, stationary. So the name itself says what I'm planning to do in this study. So pre-crack, stationary, CAE is the file name I'm using. And Frank, I'm going to email you this. You can just start with this. So create a folder in your temp drive and place that Abaqus file in there and set the work directory to that location. So when you run it, you won't have path problem. Don't do it from the downloads folder. It's going to create headache. So make sure you're in the part module. So let's create a part. We'll leave that name as part 1. or call it dog bone. (3D) deformable solid extrusion, and give it in meter scale. 2 meters is more than enough. We will see. We can always change that. So approximate size 2 is the horizontal distance. So vertical aspect ratio will be different. So it will be taken into the sketch mode. So add sketch. So we have done that before. We already have the sketch. We don't have to create the dog bone again. So add sketch. Already the sketch is there. So just say OK. And I don't want to do anything to this. I don't want to scale. I don't want to rotate or translate. Just say done. As it is, I'm copying it into this part creation in the sketch module. And say done. I'm not changing anything for the sketch. As it is, I have brought into my part creation mode. When you say done, it asks you for extrusion depth. Let's say 0.01. I don't remember. So let's say 0.01. Okay, that's good enough. That looks like a dog bone. So the extrusion depth I have given is 0.01. You want me to repeat it? Is that good? All right. So I'm going to divide this region into gauge length region or the middle region, the bottom region and the top region. The bottom region and top region will be connected to crosshead, right? So I'm going to constrain them the degrees of freedom. Only the gauge length will expand. So in order to do that, I'll partition the geometry. So tools. So if I have a datum plane, I can partition based on the datum plane. So that's the plan. Let me know at any point if you're stuck. I'll come and help you out. So tools, datum, plane, say line and point. We haven't done line and point. We have created the datum using all the other ways, I think. Line and point, we have never done that. So let's say line and point. So if you zoom in, you should be able to select the line right after the fillet is completed. You'll be able to select this horizontal line. And the next thing it's asking is select a point not lying on the selected line. So don't select the point lying on this line. It itself is suggesting select some other point. I'm going to select the opposite corner point. And it puts a datum plane passing through the line and passing through that point. So that's the datum plane I created. I'm going to use that to make a partition. I'm going to create a middle region, top region, and the bottom region. Is that okay? So I'm going to create one more datum plane. So create line and select line and point again. Select a straight line. I'm going to select the bottom line here. So that's the line I picked. Immediately after the fillet has entered, that's the line I picked. And pick the opposite point, as the point cannot lie on the same line. And that creates a datum plane. And close the datum plane creation option. So everyone has the two datum planes. All right. So go to tools, partition. So tools, partition, cell. Cell means volume here. So edge means only the line it will partition. Face means only the surface it will partition. Cell means it's going to partition the volume itself. So choose cell, use datum plane. It's asking me to select a datum plane. And once I select, say, the top datum plane here, and say create partition, it has created the line there. You can go to wireframe mode to see what it is doing. So the wireframe mode is there at the top, render model wireframe. So previously this partition, this rectangle partition was not there, only lines were there. Now it divided the partition there. Yes.
This section, different sections.
So that's the gauge length. The others are for connecting to the crossheads, right? We're going to constrain the for applying boundary conditions. So I'm dividing the regions now itself, rather than doing it in the load module. I'm doing it now itself, and I'm going to create it. So this exercise is for pre-crack. The crack I'm planning to put it in the gauge region, the gauge length region, the middle region, not in the other two. So that's why I divided this. I'll put the crack somewhere here. So do the same again. Create partition cell, use datum plane, and this time it asks for select the cells to partition, because now it has it saw that there are two different cells. There's one cell we already partitioned, and this entire thing is another volume. So that's why it's asking which cells you want to partition. You can draw a box around everything or select the bottom cell. I'm going to draw a box around everything. Everything possible. Say done. And select the bottom datum plane. Everything possible by this bottom datum plane, and say create partition, and you will see a separate volume now from the bottom. So create partition, and now you would see. So that's a separate volume. So if you go to instead of all, if you choose cells, so that's a separate volume now. And this is a separate volume. That's a separate volume. So quickly I can apply boundary conditions now. So if you make it the selection by cells, you can see the three are completely three different volumes. I partitioned them. Everyone's able to do that? All right, so let's create the sets also here, so that we can apply boundary conditions easily if we have sets. So go to tools, set, create, tools, set, create. So this is set top. So I gave the name set top, continue. And if you choose the selection by cells, so go to this drop down and make sure you're selecting the cells. And just with one click, you're selecting that entire volume. If you have something else, all or faces or something, it's going to select the closest entity to it, whatever, wherever you click. So make sure if you select cells beforehand, and then with one left click, it selects the cell that is closest, no, the volume that is closest, and say done. That's the set top. So I'll repeat that for the bottom and the gauge length also. Tools, set, create. So I'll call this set middle region. Set middle region. Continue and choose the middle region, the gauge length region. Done. Repeat that tools, set, create for the bottom region. Set bottom region, continue and select the volume. Say done. So you can quickly give boundary condition if you have sets. That's the reason why I created those partitions. So I'll go back to my shaded mode. So that's how you go from wireframe mode to shaded mode. Everyone's able to do that? All right. So that's everything about this part, the dog bone. So let's create one more part, which is a plate, which would become our crack. So the plate itself, we'll call it a crack. Somewhere we're going to call that as a crack. So let's create another part. So I'll give the name as crack, because this exercise is pre-crack. So I have to create the crack. So it's a so I'll call this 2D planar shell, deformable. So approximate size, maybe it's a small crack, so I'll give 0.2. So I chose 2D planar deformable shell, approximate size of 0.2, continue. So draw a rectangle. So crack, it doesn't just need to be a line or a wire. It has some surface. That's what I'm doing here. So crack surface is what I'm creating. So draw a rectangle and give some dimensions. So let's say the horizontal dimension is 0.02. And the vertical dimension of the rectangle is 0.01. All of those are in meters. Let me change my font size. So that's the rectangular plate I created, 0.02 by 0.01. And that 0.01 intentionally I picked because that's the entire width of my dog bone shape. So that's the 0.01 that I matched. The other one, it's slightly longer, 0.02, twice the width of the dog bone. And say done. So you just created a surface that you can call it as a crack. Somewhere down, when you enter the XFEM information, we're going to call this as a crack. So that's all the parts that we need. Go to property module. And I'll go back to dog bone shape from the parts, dog bone. So the material properties is there in the problem description. I would ask you to open this in your browser so that you don't, so that's the Abaqus fracture exercise 1. Have this open in your window and we're going to enter these properties and we'll assign it to the entire dog bone. So density, anyone knows where density is in the material property? So create, the very first icon is create material. Where is the density here? Density will be under general, right? So general density, that's 8850. And I've been consistent with the units. I'm using the meter scale. So back as consistent units, if you check, so that's kg per meters cube. It asks in density. So I'll show you where that is the consistent units. Abaqus consistent units is at the very top. So consistent units. So the density, it has to be in kg per meter cube. And everything else are being consistent with this column, the SI meter scale column. So all the properties are listed in those units. So I'm going to enter, so that's the density. So elastic modulus and Poissons, you know how to enter it. So go to mechanical, elasticity, elastic. The modulus is 225 gigapascal. So 225 E9 Newton per meter square. And the Poisson's is 0.3. And I don't have any plastic properties. I'm not giving. So I won't be seeing any necking because I'm not entering any plastic yield stress versus plastic strain. I'm straight away going to damage criteria, crack formation criteria. I'm going to explain all of this after the exercise, after the 3 exercises. I'll explain what these do. One is for initiating the damage, the other is for propagating. So when the stress, it meets this criteria, the crack is initiated, the crack is propagated. So we're going to discuss this after the exercise. We'll first enter these values and we'll complete the exercise. We're going to use the same properties for wind turbine also, the exact same properties. So we will be discussing those properties again. So go to mechanical, damage for traction separation loss. And so the traction separation loss, and there are a bunch of them. There are 6 different ways you can define those damage models. The one I have in my problem description is for max S damage, max nominal stress damage. You can see the others. There is somewhere there is max PE damage, principal strain. The very last one is max principal stress damage, and so on. And we're going to discuss all these options later on after the exercise. As of now, we're going to the max S damage. So go for mechanical damage for traction separation loss. Max S damage. S is for nominal stress. E is for nominal strain. Quad S is quadratic nominal stress. Quad E is quadratic nominal strain. And we'll look at all of this criteria. Let's just go for max S damage. And those are the 3 values that are given in our problem description. Nominal stress, normal mode, first direction, second direction. We'll discuss about those directions again. So 250 E6 320 320 megapascal. I converted to Newton per meter square. So 250 320 250 E6 320 E6 and 320 E6. And it was saying the direction relative to local 1 direction. This is the heart of the problem, how the crack initiates and crack propagates. So we'll discuss this again. So the direction relative to local 1 direction is given as parallel. So use that. So direction relative to local 1 direction, choose the parallel option. And we'll discuss what are these 2 options again. The tolerance, we'll discuss what the tolerance is. The position, it doesn't say it there. So let me choose combined. So instead of centroid, these stress calculations, it can check at the centroid of the element before the crack initiates or propagates, or at the crack tip, or at the combined. When to choose which one we will discuss. It depends on our mesh size. So let's choose combined now. Combined means whether it is at the crack tip or at the centroid of the element, wherever this stress occurs, that's when the crack should initiate. And we'll discuss all the other things. So I chose direction relative to local 1 as parallel. Tolerance, I didn't change anything. I left it as default. Position, I changed it to combined, whether it's centroid or crack tip, wherever it happens. So that's the combined. And those are the stress values I have given. Normal, first direction and second direction. Those are all the only options you will have. We'll discuss what those directions are. So that's the initiation criteria for the crack max S damage. Damage evolution. So damage evolution will be part of this damage initiation. So after you define the damage, you will have under sub options, you have damage evolution. So how should the crack propagate? That's the damage evolution. And here the problem description says use the BK method. So use type as energy, mixed mode behavior, power 2.2. So type as energy. So when I change it to energy, it should change to fracture energy here. Displacement at failure, I could probably enter it for tensile testing, but when I go to wind turbine, I will not know at which displacement the crack would propagate, right? So it's easy to enter in terms of energy because the fracture energies are reported in literature. So go to energy, and it's asking for fracture energy, and instead of mode independent, mixed mode behavior, mode independent means whether it is the mode 1, which is opening mode, mode 2 sliding, mode 3 the tearing mode, any of the modes, if this fracture energy whatever we are entering it meets, the crack will propagate. I think my problem description is asking instead of mode independent, this is more powerful. Go to BK. That's a person's name. We'll discuss that criteria. If you go to BK, then it has 3 different fracture energies: normal mode, shear mode, and the second shear mode. And we are given those values. So this from literature I got 300 kilopascal, 300 E3, 800 and 800. So we'll discuss all of this. It's pretty simple concept. So we're going to discuss this at the end. So 300, 800, 800. E3, so kilopascal. Oh, I think I have to enter the power also. So the BK law will have some power. Let me show you the BK law. We're going to discuss this at the end. So that's BK law will have the fracture energies from 3 different modes: G1, G2, G3, and in some algebraic form. And you have a power also eta. That eta is given in the problem as 2.2, and we'll discuss this later on. All of this we can get it from literature. That's why I went with the energy option. Displacement is difficult to get. You can do that for tensile testing, but others you can't. So use the power as 2.2 here. So that's the power given in the problem, and we'll discuss that. Say okay. So the same things we'll do for wind turbine also, after we discuss this, all of this entities here. So that's for damage evolution. So damage and fracture mechanics, we use them interchangeably. Usually damage means at the micro scale, where you will see voids at the micro scale, and all those voids start joining, and then it becomes crack. And when you start seeing the crack, that's when we call it as fracture mechanics. At micro or macro scale, and you can see the crack, that's when we call it as fracture mechanics. That studies fracture mechanics. But before that, damage initiation means at some location where stress intensity is maximum, where stress concentration is maximum, you would have voids develop at micro scale. That's why the damage word is used here. That's the damage here we are entering. So apart from these two, we will go to sub options again. We'll specify something called damage stabilization cohesive, and we'll be entering viscosity there, viscosity coefficient. That is just an optional parameter we are entering, just to, so 0.001. I gave a very small value. So this is there just to help me with convergence. The fracture problem is non-linear, so it won't converge very easily. And that's what it's helping me with, the viscosity coefficient. It needs to be taken as a very small value, and we'll discuss this through slides. I have it in my slides. This has to be a very small value. If it is taken slightly greater, then the dissipation, viscous dissipation will be more than the kinetic energy. Then our solution is compromised. We have to find a balance. It can't be too small, it can't be too big. So we will look at that. If it is too small, 0.0001, it might not help us with convergence at all. If it is too big, our solution is not reliable. So somewhere around 0.001, just to help us with convergence. And say, okay, we're going to discuss about all of this with slides. And that's all I have, I think, in my problem description. So the damage evolution, stabilization, Professor, I haven't specified that here. But yeah, that's the only addition there. Otherwise, I have entered everything as it is that you see here. And the same thing we'll use for wind turbine. So say, okay. So I've created a material. So I'll create a section now, right? We'll assign it to this region. So create a section, a solid, homogeneous, continue. And that's the material I have assigned to that section. And assign section. And give the name, before you assign the section, give the name as set entire dog bone. Entire dog bone. And draw a box around everything. And say done. So those are 3 different volumes are there. All of them have the same material properties. Say okay. And everything should turn to cyan color. Everyone's able to do that? So please keep saving it. The fracture problems are very non-linear. It might crash. Once we start meshing and running, it might crash. So I'm going to apply the same material properties to the crack also. So initially the crack has the same material properties, but gradually it's going to lose its stiffness based on some criteria I'm going to give. We're going to discuss that. That's the damage evolution criteria I gave. Based on that, it's going to lose. So initially, let me show the equation there, the damage evolution. So initially, it starts off with whatever the strength, Tn, Ts, and Ts, the 2 shear directions and 2 normal directions. We discussed that. Initially, the crack also, the plate we created will have the same as the dog bone, but the D that we just defined, the damage evolution, will keep subtracting, reducing, it reduces the strength in different directions. And that's how it becomes a crack and loses complete the stiffness. So initially, we'll apply the same material properties. We'll discuss the damage evolution again. So go to, instead of dog bone, go to crack. The material should already be there. So create a section and let's call it shell. We created it as a shell part, 2D shell part. So shell homogeneous, continue. So shell thickness, I'll give a very small value, 0.01. I'm leaving everything default here. And assign section. So assign section and give the name as set crack. So the reason why we're creating the sets is we're going to use them later on for applying boundary conditions. So set crack, draw a box around everything and say done. I think I gave it a section 2, right? It might give okay. So I'm applying the same section, the solid homogeneous. I thought it would ask me for shell, but it's fine. I'm applying the same section, a solid homogeneous. Say okay. So that's the solid homo, the very first section I created for the dog bone. I'm using the same thing for this also. Say okay. All right, so let's go to assembly. So I have two parts. Go to assembly. Let's bring in create instance. Let's bring in the dog bone first. Say OK. So I'll bring in the crack also. This study, the first exercise is pre-existing crack. So I'm going to assemble the crack here. So create instance. So choose the crack, auto offset. And say OK. Dimensionality of the exist. Okay, so I think I should have created the. So that's why shell and solid. We need to be careful there. So I would quickly change the crack to or dimensionality. So that's the. So I'll cancel this. I'll go back to part. Let's see whether I can change this crack to right click and I can't replace this. So 1 second. So this is okay. This is 2D and that is 3D. That's the problem it is giving me. The dimensionality is not matching. So I will create the crack again. So instead of 2D, I can't replace this. If I say edit, oh, I can change this to 3D. So right click on crack and say 3D. The 2D and 3D dimensionality problem, it's not allowing me. So go back to the tree. Right click on crack, edit. Change that to 3D, deformable. Okay. And I believe the property now will be, it still has the same property. Okay, that's fine. And now in the assembly, it shouldn't give me a problem. So create instance, bring in the crack. Okay, so now that was the error it gave me. So it's the same shell. If I created it in 2D one part and 3D the other part, it's not allowing me to model them in assembly together. Were you able to fix that? All right, save it. So it's good to get problems so we can learn more about Abaqus here. All right, so we're going to assemble. I'm going to place this crack somewhere in this gauge length, exactly in the middle. Surface cracks, which one is more dangerous, the surface crack or the internal crack? We learned it in the last class. No, it's going to be the surface crack. The reason being, so the Irwin equation. So if it's internal crack of length 2a, only half of that will be part of this stress intensity factor, whereas the surface crack, the entire length is part of the stress intensity factor, meaning the stress intensity is more for an external crack, right? The entire length is part of this. So it's almost twice for the surface crack than the internal crack. So let's do for this severe case, the external crack. So first thing is I will rotate this. So rotate instance. Select the crack. Say done. Select an axis for the rotation vector. So I'm planning to rotate by the x-axis. My x-axis is red here. So in order to rotate it about the x-axis, say the start point, I'll say 0, 0, 0. The second point, I'll say 1, 0, 0. Right? So 2 points will define the axis of rotation. And the axis of rotation in this case is in the x direction. At the first point, I'll leave it as 0, 0, 0. Enter. The second point, I'll call it as 1, 0, 0. Indirectly, I'm defining or I could pick some edge and ask it to rotate about that edge. I'm using the global coordinate system, say 100, and the angle of rotation 90, and it should rotate about x-axis. I'm okay with the position of instance. Okay, done. And I'm going to make this external crack. Everyone's able to do that? Were you able to rotate it 90? So if at all you have problem picking surfaces or edges in your geometry, look for this translate and rotate options. They should always work. So translate instance, select the crack, done. Select an axis for translation or select the point. So I'm going to zoom in and select the rightmost corner. So this is the corner I picked, that point. That's the first point I picked. The second point I would pick is something on the dog bone. So the midpoint of the gauge length, exactly in the middle. That's the end point. And the crack goes and sits there. So that's the external crack. The surface is exposed there. The crack is on the surface. Say done. And if you go to the wireframe mode or the translucent, somewhere translucent will be there. Translucent, look for a cube with global transparency. So for me, it's there at this end. So just beside the colors, the assembly defaults, just beside that, you have this translucent. So if you click that, you would see that's the crack. So it's appearing transparent, that's on that part. I still have to define it as a crack. It has some geometry there, but I haven't defined it as a crack yet. If the transparency is not looking good, you can go to this drop down and increase or decrease the transparency there. So you can see how the crack is positioned there. That's why I picked one of the dimensions of the crack as 0.01. That's the width of the dog bone there. And the length, it's almost halfway there. So the first exercise is a stationary crack, it won't grow. So save. So that's all I need to do in assembly. There's just two things there. I assembled them. All right. Step. At any point you're lost, let me know. So once we create the CAE file, all three exercises can be done very quickly. So at any point you're stuck, let me know. So go to step module. So let's create a step. Static general, continue. So 1 second is fine. Intentionally leaving the nonlinear geometry off. If you want to calculate stress intensity factors, the NLGOM needs to be turned off. So maybe I'll write in the OneNote. So in order to do this, the nonlinear geometry of for a stationary crack. So it's a stationary crack. So I'm turning off the nonlinear geometry, which is the default. 1 second is fine. Incrementation is fine. I'm not changing anything here. Everything's default. Say OK. So when you did that, automatically it created a field output. Go to the next icon there, field output manager. It already created a field output for us based on the static general step you defined. If you go to edit, it selected the selected defaults already for us, some stresses, some displacement and things like that. We are interested in the fracture behavior. So go to failure and fracture. There's nothing selected there. So go to the drop down for failure or fracture. And we will select two things, the phi LSM and the psi LSM. Anyone remembers what is phi and what is psi? LSM for level set method phi and psi. What does phi represent and what does psi represent? So I'll just refresh your memory. So phi equal to 0. So we have signed the notation here, right? Phi equal to 0 is the crack surface. Psi equal to 0 is the orthogonal surface. And if you define that, then the coordinate system, how it keeps track of the crack is, if this is phi and that is psi, all the other nodes, there will be signed distances now from the crack surface. So for example, this particular node 1, it is at a distance of 0.25 and it is on the top of the crack. On one side you have positive values, on the other side you have negative values. So node 1 and 2 has positive phi's and node 3 and 4 it has negative. And similarly for psi also, on this side, on this side you have negative psi. On the crack side you have negative psi. On the other side, where there is no crack, the psi is positive, and that's how it keeps track of where the crack is. And we want to output this, and we can look at the crack growing. For the first exercise, you won't see the crack grow, but when it updates, we can see those things. So select the phi LSM, psi LSM, scroll down. I think state or field. Yeah, status XFEM. We'll discuss this. So status XFEM in the state or field. What it says is if the status XFEM is 0, means the crack has not started. Status XFEM, if it turns 1, there is crack. At all the locations where status XFEM becomes 1, there the crack has already propagated. So just to see where the crack is, status XFEM, and say OK. So it created a field output, and I went and added 3 things: the phi LSM, the LSM for level set method, psi LSM, and status XFEM. For stationary crack, I want to calculate the stress intensity factors. So only for this first exercise, pre-existing crack stationary, go to history output manager, which is the third one there in the step module, the third one. It's already, so there is some history output created, edit it. The history output it is writing is for the whole model as of now. And usually what history output consists is the energy, all the energies, the kinetic energy, dissipation energy, and all those energies. Instead of the whole model, we'll go to the drop down and choose crack. Oh, we haven't defined the crack yet. The drop down, it can't recognize the crack yet. We just created a part with the name crack, but I never defined that that is the crack. So we'll come back to this and we'll define the stress intensity factors. We want to write the stress intensity factors. So I'll come back to this, cancel. So save changes, no. So I'll close this. So somewhere I have to define that that is the pre-existing crack. And that's the most crucial step. We'll come back to this history output. So go to interaction. That's where you define that that is a crack. So go to interaction module. So special, at the very top you have special. There is a crack there. Go to special, crack, create. And those are the 3 ways to create a crack: contour integral method, extended finite element method, and the debond using VCCT, virtual crack closure technique. The other 2 methods, they're pretty old. They're really good for pre-existing cracks. Already you know the crack direction, where it exists, where it forms. For example, this particular exercise, you can use those. And it depends heavily on mesh. Only if there is an element going in that direction, along that element edge, crack will form using this method. Extended finite element method is, it becomes independent of mesh. Of course, you need to have decent mesh size. And then even if there is no element edge, it can go diagonally in the element also. That's the extended finite element method. It doesn't need a direct, though we are doing the pre-existing crack, we're going to quickly change this to no crack existing, and the same study should work. So choose XFEM, extended finite element method. Anyone remembers what's the biggest highlight of extended finite element method? Say continue. The first thing it asks is select the crack domain. That's the biggest. What it wants to know is where it needs to create the phantom nodes. So that's the crack domain it's asking for. So when I select a particular region, for this case, I will select the gauge region. So it's going to create extra nodes called phantom nodes along with my real nodes. After I measure, I have real nodes. Whereas this gauge region will have some additional degrees of freedom in form of phantom nodes, right? We discussed in the last class. So when it asks you to select the crack domain, go to sets and select the middle region, highlight selections in viewport. And when I say continue, I think a green region will form. So continue. Okay, once I fill this menu, that region is called enrichment region. So at that location, in this volume, all the real nodes will have phantom nodes also. So we'll see that appearing in green in a second. So that's the domain that I picked. That's the advantage of extended finite element method. It creates phantom nodes also for us. So that's the region we picked. So allow crack growth, uncollapse this. So it's a stationary crack. The first exercise we are doing is for a stationary crack. It's not going to grow. We are doing this for just measuring the stress intensity factor. So uncheck the allow crack growth. That's going to be the only difference. For the next exercise, I'll come and allow the crack growth, then it will be a propagating crack. So the first time when you build this file, if it runs for the first time, then running for the other 2 times is very easy. So uncollapse the allow crack growth, crack location, and this is where I need to define the pre-existing crack. If I don't define this, it's going to assume there are no pre-existing cracks, and it will create, that will be the third exercise. I'll leave this empty. The third exercise of this dog bone is no pre-existing crack, right? I'll come and change this and rerun the analysis. Then it will create somewhere else, not at this location where I put the crack. It will create somewhere at the fillet region. So first exercise is pre-existing crack. So I'll choose the crack location. Go to this edit, which is the arrow there. And so if you have the set crack, you can select the set crack. If you don't have the set crack created, all of you, are you able to see the set crack? Anyone who doesn't have the set crack? So that's the advantage of setting the groups beforehand. If you don't have the crack before, if you haven't created the set before, what you could do is, so uncheck this region to select the entity to closest, and you can zoom in and click close to that region. As of now, it picked the first region. I can go to next. I can go to next, and then it picked the correct region. That's difficult to pick with the internal sets like that. That's why we created a set beforehand. If at all you don't have one, so remove this select entity to closest first. So remove the select entity from closest, and then you keep clicking and say go next, next, next until you see the one you want to create. So I'm going to go back to my sets. So the crack location, I'm going to take it from the sets, the set crack, continue. So we'll be coming and changing this menu for the other 2 exercises. And this is the core for this is where we're defining the crack. The crack 1 is the name. The name I left it default crack 1. And that's going to be the name I have to choose in the history output. So crack 1, say OK. And now if you observe, as I mentioned, we put the green points there, just to show me that only this region has those green points, just to show me that that's the enrichment region, right? In the enrichment region, what happens? So you have phantom nodes superposing the real nodes. So you have, say, at this location, there are solid nodes and also the unfilled nodes. But as the crack criteria is met, the phantom nodes and the real nodes, they can separate now based on the cohesive law. And the phantom nodes have additional degrees of freedom, which are because of this Heaviside function and this asymptotic function. The Heaviside function is going to take care of the jump at the crack surfaces, right? At the same location, you have two displacements, right? At this location. I don't know why I'm not able to write on the PowerPoint. So the enrichment region at this same location, now you have at that location, you have two different displacements. There is a jump in displacement, and that's taken care of this additional degrees of freedom. Heaviside function multiplied to the additional degrees of freedom. The asymptotic function is at the crack tip. The stress singularity is taken care of this asymptotic function, which is a function of the radius of the crack tip and the angle there at the crack. So f of x asymptotic is at the crack. H of x is at all these locations. The H of x Heaviside is applied at all these locations because there is a jump there. So that's the additional things applied only in that enrichment region. So only in this green region, you have the phantom nodes and the real nodes. And the phantom nodes have additional degrees of freedom, and they can move separately from real nodes if some criteria is met. Everyone's able to do that? So the same thing what we did, we went to interaction module, special crack. Whatever we did, it should be editable, right? So if you go to assembly, if you uncollapse assembly from the tree, uncollapse the engineering features, that's the crack you just defined. In case you want to modify it, you can right click on it and modify, right? That's where it's stored in the tree. And now let's go back to our history output. So from interaction module, I went to the step module, and in my history output manager, now I can edit the history output created. And now instead of whole model, I choose the crack. And now the crack one that I created, already defined the crack one in interaction module. And that's there now. Previously, this was not defined. So I couldn't pick the crack one from here. And what I want to do for this exercise is the stress intensity factors. There are other things it can do. I'm planning to do stress intensity factors, which are the K1, K2, K3, and the maximum energy release rate. We have crack initiation criteria. We have a bunch of them. So maximum energy release rate. Okay. Oh, I think I need to give number of contours. So give the number of contours as 5. So history output, go to step module, history output, change the domain to crack, not the whole model. And that's the only crack you define. You can have multiple cracks, right? That's you can write for each individual crack. Those are the stress intensity factors K1, K2, K3, which are nothing but magnification of remote stresses. How they are getting amplified at the crack. That's what you want to write. Say okay. So you can do this only for stationary crack. And that's why I'm asking this to be written in the history output for this exercise. So keep saving it. All right. Go to load module. I don't have to do anything in interaction. All I needed there was define the crack. So go to load module. So this is where I have to apply, I have to constrain one of them to the bottom crosshead and I have to pull the other, right? So in the load module, At any point you're stuck, let me know. I'll come and help or I'll repeat. So in the load module, so create a boundary condition. There's a second icon there. I can create this in initial step. So the initial step means I can't have non-zero magnitude, right? If I create a boundary condition in initial, mechanical, symmetry, anti-symmetry, encasted, continue. And if the sets opens, you can select the bottom region, dog bone, entire bottom region there constraint. Continue. That's the reason why I created the sets beforehand. And encasted all the degrees of freedom. I'm constraining. And say OK. Everyone's able to do that? So usually even in our MTS machine or Instron machine, we'll have bottom cross-thread stationary. So that's going to grip the specimen without moving. Whereas the top one, the cross-thread pulls it. And you can do that either by giving displacement to the top portion, or you can specify the load on the top. So I'm going to do the displacement. And I would do it slightly differently so that I can introduce a new thing to you. So the plan here is I want to create a reference point at the top region, and I'll apply displacement only to that reference point. And I will tie all the top region to that reference point. So all of those are indirectly pulled with that same displacement, right? So that's the plan. You could just select the top region and apply the displacement in the y direction, which is 2, y is 2 direction. So in second direction, you could do that, but I want to teach you the equation, how to create an equation. So let's create a reference point first. And I want to create it exactly in the center so that there is no rotation. So before I go to creating the reference point, go to this query information. Point or node, and select the first point and say done, and select the second point there exactly in the middle. Done. And those coordinates are written in the menu here. The first one has the coordinates as 0, 150 e minus 3 and 10 e minus 3. And the second one has 0, 150 e minus 3 and 0. So if I want exactly the middle of these two nodes, what should be my coordinates? Right? What is the direction that it's changing there? Z, right? That's the Z direction. I want to place my reference point exactly in the middle. So I'll leave the X and Y coordinates the same. The Z will be the average of these two coordinates, which is 0 and 10 average, which is 5e minus 3. So go to tools, reference point. So tools, reference point, and it's asking for XYZ coordinates. I'm going to enter the X as 0, Y as 150 e minus 3, and the Z is the average of the two nodes, so which is 5e minus 3. And I'm expecting it to be placed exactly in the middle here. So if I say enter, so that's the reference point it created exactly in the middle there. My font size is messed up slightly. So it's exactly in the middle of those two nodes. Everyone's able to do that? So the reason for doing that is I want to apply displacement to that node. So go to create displacement. So create boundary condition. And I don't want to do this in initial. the problem with creating boundary condition initial is I can't give non-zero. I can only give zero boundary condition in initial. So I'll create this in step 1. And I will choose displacement rotation. Continue. And for the region, I haven't created a set for the reference point. So I'm going to dismiss this. When it's asking me to select a set, I'm going to dismiss this. I can select it from the viewport. So zoom in close and select just the point. If the entire face is getting selected, maybe from the selection, go and pick only the reference points. And now it should pick only the reference point and give the set now. At least now you can create the reference point. Set RP. So selected the reference point and set RP. So be careful when you're selecting to make sure you're selecting what you want, not the entire face or edge there. So go to the selection and choose the, I could have left it as vertices also, I think, or I went to reference points and then there was no ambiguity. It picked the reference point. And I'm creating a set called RP and say done. So for the set RP, I'm going to use the global coordinate system. I'm going to constrain all the degrees of freedom as 0 except U2. U2 some positive value, say 1e minus 4 meters. So that's a lot. So 1e minus 4. Yes.
Why are we putting U to S1 minus 4?
That's how I'm simulating the tensile test. Like the crosshead is pulling the specimen, the top portion is pulling it. So I'm applying it on the reference point. That's the displacement I'm applying on the specimen. You could do it through force. The tensile testing, you will have 2 modes to do. Either you control the load or control the displacement. The most often method is the displacement, because the strain rate you can control. That's the strain rate per second you can control there if you give displacement and say OK. So now you would see an arrow there applied to the reference point. Someone is able to do that? Are you able to see an arrow there for reference point? I'm not sure 1e minus 4 should be sufficient. We will see. Or maybe I'll change that to 2e minus 4. So I'll go to edit. So go to manager, edit. I'll change that to 2e minus 4. We'll come and change this if we don't see the crack open completely. So I gave it to some reference point, but I haven't tied that reference point to the top portion at all, right? That's some reference point which is free to move without any connection with the top specimen. And this is what I wanted to show. How do you constrain a degree of freedom for this reference point and this top portion? And we do that by creating something called equation in interaction module. Go to interaction module. So the third one, we haven't used this third one before. It's creating constraint. So create constraint. And you have multiple things there. Tie, rigid body. I think Alex, you are using one of this, right? For your impact problem, you would probably use tie. Let's use equation here. Continue. And it gives me a table to fill. I'll first fill this and I'll explain what I'm filling here. And if you don't know what we are doing here, there is a bulb here. So if you click on this, so it's expecting something like this. So I'll enter and I'll explain what I'm filling here. So the coefficient as 1. Set name, I'll choose dog bone top region. If you can see dog bone set top, that's the name I gave. Degree of freedom only 2. So I can choose which degree of freedom I want to constrain. The coordinate system global. For the next row, -1, I'll choose set reference point. So set reference, that's the way we create sets. So we can do something like this equations and the same degree of freedom too. So what I have done here is, so I have written 1 times the degree of freedom means 2 means U2 of dog bone top region minus, or say plus of -1 times the second degree of freedom of set RP reference point equal to 0. That's the equation I entered indirectly. Indirectly, what I specified was the displacement of second direction displacement of dog bone top portion is equal to the U2 of the reference point, and I already gave the U2 of reference point as some 2e minus 4. So now I'm applying it everywhere in the top region, right? Are you able to see that? And this equation can be used not just with the displacement boundary condition. You could do that with the forces also. Yes.
Why is the degree of freedom change?
It's in the y direction, right? So my try. So y is 2 here. So let me increase the font. Viewport annotation options. So that's y. So x is 1, y is 2, z is 3. So that's the advantage of this equation. A particular set's degree of freedom can be constrained. And tensile testing, you could think of applying this in the direction of pulling. You can apply the degree of freedom constraint. So in interaction, we have entered an equation. We constrain the degree of freedom. And load, we have already completed the load. That's all that is needed for tensile testing, right? So I've gave displacement in the y direction. So mesh. So all we have to do is mesh and run the analysis. I would ask you to save it before you mesh it. The chance of it crashing is high. So we're going to mesh by part and choose the dog bone. We don't have to mesh the crack. We already defined that it is a crack. Whatever is happening in assembly, only that is part of analysis. Whatever is happening before that, that's not part of the analysis. So give a seed. So the reason why I divided them into different regions is I can give different element sizes. So here there is going to be a crack. So I want a very fine mesh here. The other regions don't have to be that fine. So first give a global seed part of I'm not sure. Let's see 0.01 how it looks. That's probably a little too coarse. I'll go with 0.05. That looks okay. So 0.005. Global seeds means everywhere it is being applied now. I can overwrite it. So initially what I did, I specified for the entire part some decent mesh size. But in this gauge region, I'll come back and define a finer mesh. So I'm overwriting only in that region and say okay. And so the very next one, you have done this for process problem, seed edges. Instead of global seeding, we'll do seed edges for the gauge region. So choose seed edges. And we already created sets. So go to sets here and choose the middle region. Continue. Only for the middle region, I'll apply slightly finer mesh by size, maybe just finer 0.003. I'm applying slightly finer mesh there. So 0.003 and say OK and dismiss this. So you can see I have a slightly finer mesh here. It's in a different color also. Whereas the other regions I have a slightly coarser mesh. So that's why I partitioned. So I could do all of this. Even meshing I can do separately. We're done. So the color coordination here, I have some green, I have some yellow. That's coming from whether it's a structured mesh or not. So go to this mesh controls, assign mesh controls, and draw a box around everything and say done. And you would see the colors. I will leave it as hexahedral shape. As is, I will leave it as is. So the green region, it will try to do very structured mesh. Other regions, which has the curve. So it's difficult for any software to create a very structured or organized mesh if it has curves like this, the fillet region. So usual option is to sweep. If sweep also is not possible, then it will do free mesh. It won't look that good, and the aspect ratio won't be that good. Structured will have a really nice repetitive pattern of elements. The next best is if you have curve, you have no other option but to go for sweep. So I'll leave everything default. I haven't changed anything. I'm just showing you this will be very structured mesh, and because of fillets, this region won't be extremely structured. Yes. Bottom up is you can mesh one of the faces and then propagate it. So you need to have some mesh beforehand and then propagate it throughout this bottom up. So I'll leave everything default here, say OK. I haven't changed anything there. So mesh element type, which is the S4R. S4R, for the entire region. So set entire dog bone region. So I have the set or you can draw a box around. You cancel this if you don't have a set. Draw a box around everything. So I have a set created already. So continue. I'm going to leave it as 3D stress. Standard linear. I'll remove the reduced integration. I'll explain what's reduced integration. So integration points are going to be, so for a C3D8. So hexahedral will have 8 nodes. C for continuum is a solid. Continuum means a solid. 3D and 8 node. 8 node is for hexahedron. There are 8 nodes. Reduced. So for this, 4 integration points will be there for this element. We'll discuss about integration points. The very last class, Gaussian quadrature will discuss. Reduced integration means instead of 4 integration points, 1 integration point will be there. It saves time in few situations. So C3D8, that's the element type I'm using. Say OK. And I'll mesh the part and say yes. So you can see I have coarser mesh in not so important region, and where I have the crack, I have a very nice structured mesh. It's fine enough. I can go finer than this, but we'll spend more time with conversions. And that's the structured mesh in the important region. Everyone's able to do that? All right, so let's create a job. So go to job module. So save it. It might crash. So create a job. So give the name, proper name as a pre-crack. We're going to do this two more times, right? So this pre-crack stationary. stationary. Continue. And everything default here. And go to job monitor and say submit. So if everything works well, then we can use the same CAE file, modify it for propagating crack and no existing cracks. So input processor file completed successfully. I didn't miss out any like material assignment or I didn't miss any. So if you remember, I didn't mesh the crack at all. So it is not complaining that I didn't mesh the crack. So go to monitor. Within 1 second, it complete. There was no convergence problem. It was a stationary crack. It did it really quickly, no problems. And go to results. Anyone still waiting for the result? Has the job completed successfully? All right. So go to stress contour. And let's run the animation. And if it's too fast, reduce the speed. And that's what is happening. It's not growing. It's a stationary crack. So the length of the crack is staying the same. The only thing we wanted is to write the stress intensity factors, and we'll look at that in a second. We'll see that. So let's look at the other things we have written. Phi LSM. Phi LSM should indicate where the crack surface is. And if you zoom in, so the crack surface is green, which is phi equal to 0. On one side of the crack surface, you have red region. On the other side, you have blue region. The blue region is negative. On the other side, I have positive. Red region is positive. So it's indicating the location of the crack. You have a red region. The closest nodes, the top ones have negative phi, and the bottom ones have positive phi, and the crack surface has green. Let me change that to psi LSM. Psi LSM is showing the orthogonal surface to the crack, and it also has that red and blue. And we also wrote status XFEM. Status XFEM, everywhere it is blue. At all those locations, it's 0. Only the locations where it is 1 is shown in red. That's where the crack is. Right? All right, so let's save this. We still have 7 minutes, so we'll quickly run the propagating crack. So I'm going to stop this animation. Go back to my job module. So doing this for the first time was time taking. Now I have the CA file. I can quickly change it and do the second exercise. Oh, I forgot to show the stress intensity factors, right? So we did this pre-existing crack to measure the K1, K2, K3, and they are part of. So let me go back to my results again. And if you remember, we have written it as history output. So if I go to result, history output, and you would see that if you scroll down, you would see the stress intensity factor, K1, K2. So I have K1 here, and then K2 is for second mode, which is the sliding mode. So that's K2, and there is K3. So it's writing for crack, only the crack region it should write. So let me plot one or two things. So stress intensity factor, say K1 I'll plot. I selected, say I asked it to write 5 contours and it's writing for 4 integration points. So there are 20 of each. If I say plot, again, I have font problem. So the stress intensity factor, that's how it's changing at different integration points of the same element. And K2, so if you observe K1 will be high. Let me change the font size here. So it's pretty high, 106 in megapascal, 10 power 6. And it will have the units of megapascal, square root of meter, right? It has the multiplication of square root of pi a, sigma times square root of pi a, where a is the crack length. So m megapascal square root of meter, and it's somewhere there. Whereas if I have plotted result history output, if I have plotted some K2 and K3, they'll be slightly smaller, I think, because it's a tensile test. Only in that opening mode. So I selected a few things here, K2, and say plot. And I'm plotting on top of this. So K2 will be somewhere. So if I change the axis to say 0, so 0 will be too small, I think. So I will go to 0.09. So somewhere here K2 will be there, K3 will be there. So you can see how much the stress amplification is based on these points here. So that's how you find the stress intensity factor, and the K1, for K1 you can always compare. The Irwin equation is extremely accurate. So that's the Irwin equation within 1%. So only for K1 we have this really accurate formulas. K2 and K3 they're not that accurate formulas there. K1 is the most dangerous and the most common, the opening mode, because of tensile load, and that's what our problem involved, tensile loading. All right, so save the CAE file. We'll do the crack propagation in the next class. I think it will take 5-10 minutes. I mean, the editing the CAE file will take only 1 minute, but it will be a non-linear problem. The crack is propagating, so it will take 5 minutes to run. So we'll do that in the next class. So save this or email it to yourself. We'll quickly modify this to change this to a growing crack, and also we'll remove the crack and we will see where it initiates. And it initiates near the fillet region. No pre-crack, and we'll do the wind turbine using the same methodology. We'll do the wind turbine only for the third case, no pre-crack. We'll do the wind turbine, and we'll discuss it in the next class. The most important thing is this criteria, initiation criteria, and that's the initiation criteria we actually give. We'll discuss what that criteria is in the next class, Monday. All right, we'll stop here. So majority of you voted